Okay, let's go ahead and get started. Welcome to this session of the National Math Summit. AMATIC is proud to present Scott Adamson speaking about engaging students to actively learn rigorous mathematics. Scott was a high school teacher in a previous life and has been teaching at Chandler Gilbert Community College for 23 years. So hopefully hopefully I know he has a lot to share. So we'll go ahead and turn the time over to Scott.
Thanks, Laura, and welcome everybody. This is fun and of course different, as this whole year has been different, that I'm going to present some information about actively engaging students to learn rigorous mathematics. As I can't see you, I can't hear you, I can't interact with you in those ways. So I'm going to do my best to tell you about actively engaging students, but also I will engage you as best I can when those moments come. Here is the idea. I'll just give you 10 seconds to read this. And I hope you're wondering, what the heck is Lightning McQueen doing here? Well, of course, if you're going to do rigorous mathematics, you've got to have Lightning McQueen. Now, just a quick connection to who I am. I'll just give you this chance to look at some pictures. Yes, I'm married. I have a granddaughter. We have a foster son who's turning 4. I have 4 grown married kids. And yeah, I've been to high school. Look at that. But let's do it. Let's talk about rigor. Now, the first thing that so many people do in this world when they want to know about an idea, they Google it. And so I'm going to Google rigor. And here's what I find out. First of all, there's a medical definition. A sudden feeling of cold with shivering accompanied by a rise in temperature. Now, maybe in some of our classes, students are feeling the rigorous nature of our courses because of this. But then, of course, there's other definitions as well. Quality of being extremely thorough, exhaustive, or accurate. How about this? Demanding, difficult, or extreme conditions. To what extent do these definitions connect with our ideas of rigor in mathematics education? And I love it when Google gives us a little history. This is mentions of rigor over time. And I'm just going to make a claim here. It's probably wrong, but I'm going to say that the increase here is because math educators have been talking about rigor in the last maybe decade or so, particularly more than in the past. So what do we mean by rigor? Well, if we take it to be this demanding, difficult, or extreme conditions, my experience as a student was rigor was something like this, like do all those integrals. Oh, wait, let's make it more rigorous. Do more integrals. No. Let's make it really rigorous. And rigor becomes demanding, exhaustive, thorough, and challenging in this sense. But is that what we mean by rigor? So what is rigor in mathematics really? So if you would just we'll take maybe a minute, will you just throw into the chat a word, a phrase, an idea that you might want to include if we're going to define rigor in a mathematics education context? Creative struggle. Woo, here they come.
And just a reminder, set your chat to all panelists and attendees.
Contextual hydraulic, critical thinking. Yes, deep understanding. Knowing why, not just what. Comprehensive, I like it. Yeah, so I hope that just challenge yourself in this moment as we move forward to consider if we're going to have a definition for rigor, And then we're going to create our courses, our lessons, our tasks, our assessments to be rigorous. What shall we mean when we say rigorous? So we're going to take you through a little exploration from the Dana Center. So as many of you probably know, the Dana Center at University of Texas, Austin has been working with pathways, meaning does everybody need to follow a mathematical pathway that leads to calculus? Or could there be pathways that lead to other disciplines, data science, statistics, quantitative reasoning, etc.? And what Dana Center reports is this: among the things we have learned, one concern stands out. Changing mathematics curriculum away from an emphasis on algebra, the traditional algebra path to calculus, may lead to less rigorous courses. Okay, well, to remedy this situation, we just ensure that elements of rigor are incorporated into all courses. But check this out. We don't want less rigorous courses. We want elements of rigor incorporated into all courses, but there's a problem. There's no consensus on a definition of rigor. So how do we address this issue if we don't know what rigor means? And so the Dana Center did some research, did some work on this issue, and they came away with 4 kind of common views. This is not to say this is what the view should be. This is not a claim that this is the direction that we should go. It's just a claim of this is what we've observed when we talk to people about rigor. First, view number 1, rigor is the use of logical deductions from stated hypotheses to prove theorems. And my image there is just to give you an idea of like walking through the quadratic formula derivation could be rigorous in the eyes of some. Or another view, adhering to traditionally prescribed content. Math departments often determine course content by committees, and to be inclusive, we end up with this long list of topics that must be covered in a rigorous course. And the image there is just some snapshots of a common table of contents from, say, a college algebra setting, and you can see some of the traditionally prescribed content that we would have, adding and subtracting rational expressions, or graphs of functions would be involved in a rigorous course. View 3, rigor is synonymous with increased difficulty and more challenge. So a rigorous course is an advanced course. There's comprehensive presentation, lectures on all possible topics and techniques. There's high stake summative tests, and there's low pass rates and low grades often in these challenging courses. And we see this even with our K-12 level textbooks. There's advanced math, or there's math for gifted students. And of course, in our graduate level, there's advanced calculus, and that's what makes things rigorous. And if we look at an exercise set from many textbooks, there's sections that are called getting started, there's practice, there's problems, and then the rigor, there's explorations and challenges in some of these advanced books. So that's a view of rigor. Or here's the 4th one and the last one that Dana Center reports. A rigor idea would be rigor in college algebra. The college algebra path to eventually maybe calculus is rigorous, and so college algebra and rigor are often used interchangeably in this view. College algebra stands as a proxy for rigor, in part because the skills developed in the course may open many other mathematical options to students, and because mastery of algebraic skills signifies readiness to proceed with a student's mathematical education. So this image is just to show that there's often this this pathway of you can choose quantitative reasoning in these areas, you can choose college algebra in these areas, but the college algebra pathway is the rigorous one and the other is not. I'm not saying this is right, I'm saying this is a view that has been observed. In fact, this view can be a problem. Using college algebra as a proxy for rigor unnecessarily limits the conversation about rigor to only one area, mathematics. When college algebra is used as a proxy for rigor, mathematical modeling, geometric and numeric methods, statistics, quantitative reasoning are often labeled, therefore, as not rigorous. Yet we know that those courses can be rigorous. The ability to perform algebraic manipulations, a primary objective of college algebra, does not provide clear information about what rigor is. So understanding college algebra as equivalent to rigor is not necessarily going to solve this problem about what rigor means. So the Dana Center has asked the question, what is rigor really? And borrowing from some previous work, they put out this idea of rigor that I would like to follow as we proceed today. So what is rigor? Procedural fluency and skills is still part of rigor. We want students to have fluency in the mathematics that they learn. But add to that an additional requirement of conceptual understanding. Add to that some productive persistence to make sense of mathematics. And add to that some application. When am I ever going to need to know this in my life? Kind of idea. Add to that some application, some problem solving. Together, those four things make up the strands of a rope. As, yeah, thank you, Nan. That's from Adding Up in 2001, that image of rigor involving all of those aspects. And the Dana Center uses this quote: students use mathematical language to communicate effectively and to describe their work with clarity and precision. Rigor involves students using mathematical language to communicate effectively and to describe their work with clarity and precision. Students demonstrate that what they have done works, when it works, and why. Somebody in the chat said exactly that, to know the what and the why. Why would that procedure be used in that time? Why is it appropriate? And then the student can answer the question, how do we know? So as we move forward, I would like us to kind of focus on this definition of rigor with the four strands, the four pieces to make rigor complete. Now, this group, the National Math Summit in 2018, promoted a similar attention to rigor, attention to precision, structure, patterns, inference, interpretation, reasoning, mathematical habits of the mind, ways of thinking about mathematics, helping students to develop a mathematical identity. And in this quote, in a rigorous course, students are asked to struggle with real non-routine problems in context, identify strategies to solve problems, communicate about mathematical ideas with clarity and precision. Sound familiar? And justify their solutions. So if we put this lens on, and this is where I think it would be really important for all math educators in all institutions, K-12, higher ed, to have this idea of rigor. And then as we make decisions about curriculum, about assessment, about lesson design, we would do so with this idea of rigor in our minds. So to give you an example of just that, I have a lesson I would like to share with you. Now, we don't have time to dig into it completely, but what I hope is that at the end of this time, you will feel a sense of what I would claim, this is just my style, my creation, my style of what a rigorous lesson / task might look like. And it begins with a 3-act task. And maybe some of you have experienced, this has been out there now for several years. Folks like Dan Meyer have made the 3-act task popular in math education, where Act 1 takes a context and kind of leaves you with a little bit of a cliffhanger. Check this out.
Was jumping Carburetor Canyon.
Jumping Carburetor Canyon? No way.
Yes, way, you remember. You was there too.
What?
Ready, buddy?
Ready?
All right, Dan. Get her done.
Well, what happened?
Well, what happened? I don't know if you could hear the sound very well, but in this little clip called Mater the Greater, Lightning McQueen blasts off. He's going to jump across Carburetor Canyon, and the clip stops with, well, what happened? So I'm going to ask you
Was
again,
jumping
will you jump into the
carburetor
chat?
canyon.
And there's another framework that I've seen mostly used in K-12, but we'll ask students, what do you notice? What do you wonder? So in the chat, will you throw in, what do you notice, mathematically speaking, and what do you wonder as you see that clip? I'll give you a moment to throw those in. Yeah, Teresa, it's probably the big question. Does he make it to the other side? Modeling, yeah. Will he make it? Oh, that's good. We're starting to quantify this. Is he halfway up? Are there extra rockets to fire? I love it. Yeah, waiting for the coyote to come. That's a different cartoon, I think. Yeah, that's a good question. How accurate is the graphic with gravity? There's all kinds of things that this clip might potentially make a student notice and wonder. And at this stage of the game, by the way, I want every thought out on the table. Now, of course, as the instructor, I'm going to try to corral some of this into a focused question so that we can pursue some mathematics, maybe some rigorous mathematics about the situation, but just to have an opportunity to engage and get the students' brains thinking about stuff like gravity and yeah, how far across is it? There's all these questions that might come up. Now, as you can do, I was going to just share with you, I'm working, it's still a work in progress. It's mostly finished, but I want to tweak it some more. But I've created a Desmos activity about this, given the fact that we still have some online, but this can be done in the classroom as well. But thinking about my online courses this summer, I'm working on a Mater the Greater Desmos activity. So if you're interested in this and want to help me make it better, just email me later and I'll be happy to share this with you. All right, then this leads into Act 2. And Act 2 is where some of the questions, not necessarily all of them, but some of the questions that students have can be answered. For example, maybe you would tell students something like this. The length of a sedan. Now, understand, I'm fully aware. I want you to be aware that I'm aware that this is a cartoon. And it brings up a very important question in my mind. And the question is this. Does Lightning McQueen, given the fact that he's taking such a dangerous journey here, does Lightning McQueen get auto insurance or should he get life insurance? That's a really non-mathematical question, but it's an interesting one. But anyway, we're going to pretend that Lightning McQueen is an actual sedan. I just Googled sedan and found out that the average sedan, I think it was 184 inches. Now in this image, that little blip of Lightning McQueen is 0.079 inches. So I might just leave that with students for a while and let them work. And one of the things is I saw somebody asked about, thank you, Frank, yes. We can do some work to generate some measurements like how far is it across Carburetor Canyon? Well, when you measure in my image, I would have students print something out, we give them something to work with, but they might measure that distance to be 11 inches. Proportionally speaking, in real life, cartoon Carburetor Canyon, it's 25,620 inches, which is a couple thousand feet, which is about 4/10 of a mile. So it's a 4/10 of a mile horizontal journey across Carburetor Canyon. So maybe that would be something of interest and of use for the students working forward. All right, then I just bring this in for those of you who may be my age and remember this, but do you remember Evel Knievel? He jumped across the Snake River. Well, he tried to jump across the Snake River Canyon in this rocket ship thing that he had created. And that distance was 1,600 feet. Remember, with lightning, it's about 2,000 feet. So if we want to kind of bring this to some kind of real life thing like Evel Knievel, we might say, yeah, this is realistic, even though it's a cartoon, fully acknowledge that. Yeah, there's old Evel. You might remember his parachute deployed a little early, and he, as you see in this image, he crashed on the left side, left bank of the canyon and did not complete the jump. Anyway, that's side detail. All right, so thinking about rigor, thinking about, yes, procedural fluency and skill, yes, conceptual understanding, yes, problem solving application, all those things. I'm going to ask you to throw into chat. If you are working with students, and let's say that the big question that we all agree to answer is, does he make it? Let's make the does he make it across the canyon? Let's make that the big question that we want to pursue. And let's say that we agree as a class that a quadratic function formula model would be a good approach. Let's just say we make that connection after some conversation. So before I move you on to the next slide, I just want to pause. What kinds of questions could we ask students as they're thinking about this modeling? Will you throw it into the chat, some ideas you might have? Jason, I love your thought there. Yeah, love it. We might want to think about the vertex, huh? Yeah, what is the maximum height he could achieve? How fast was he moving? Or maybe how fast would he need to be moving? Yeah, let's just get it into Desmos and model it. I love it. Yeah, or go old school, copy it to paper and do some folding to get some symmetry ideas. Excuse me. Yeah, can we get some ordered pairs? Sure. Yeah, so many things that we could do with this, I think, in my head anyway. So for the sake of this presentation, we're gonna kind of slow it down and just tackle some specific things here together. But let's suppose we're in the classroom, and I like to, in an active way, my students would be active, well, back in the classroom days, which we will be in again soon. My students in my brain right now are working on this, they're thinking about this, and they maybe have a feeling, even if I've orchestrated it a little bit, they have a feeling that as a group, we've collectively decided, how shall we model this? Quadratic models, will he make it? And we're gonna move forward. But I'm gonna do this. I'm thinking about this at the end of a unit, let's say, and I'm gonna let the students decide. Given that the goal is to create a quadratic model, which form are you going to employ? So maybe we've studied factored form, vertex form, standard form. Which one would you choose and why? And I'm going to ask this question too, because whenever we're modeling, whenever we're looking at graphs, I want my students to be super duper crystal clear on the quantities that we're dealing with. So I want you to just ponder this for a minute and throw into chat. Just, I know you may not have a time to think about it greatly, but do you have a gut feel, factored vertex or standard form? And put in the chat, please, what do the quantities X and Y represent? And just as a reminder, oh, I don't have it yet. Hold on, it's on this next one. I've labeled the vertical axis as Y and the horizontal axis as X. Interesting. Anyway, throw it in there, please. What form of a quadratic would you use? And what do the two quantities represent? Throw it into chat, please. Christine, flip a three-sided coin and do one, huh? Or if you want to throw in the, what do these two quantities represent? Vertex form. Yeah. X is time, Y is vertical distance. Somebody else said X is a horizontal distance, Y is a vertical distance. Any other thoughts? Yeah, can't decide if X should be a time or a distance. Yeah, that's a good point. Maybe all three models. So imagine in a classroom, maybe some students will go factored, some students will go vertex, some students will go standard. And then with conversations, we can talk about the advantages of the three different models. Maybe we could have students convert from one to another, working on some procedural fluency, but in context and with maybe some meaning that might be useful. Yes, Nancy, parametric model, bringing time into both the X and the Y components. Wouldn't that be interesting? Yeah, I think, as I've thought about this problem for many, many months now, I think that this context can take us lots of places. But for the current moment here on a Tuesday morning for me in Arizona, we're going to go with this. The quadratic model that we're going to create is a model of Lightning McQueen's position on this, in this really, it's a plane. We're just kind of looking at that two-dimensional view here. His position horizontally left of the ramp and vertically above the ramp, let's say, above ground level. So X is not going to be time in my example here. X is going to be a horizontal location measured in feet, and the vertical is a vertical position in feet. So they're both feet. So let's imagine students working now. And I'm just going to play, I just made a quick video of what it might look like. Students are working and they're modeling, and I'll show you the guts of Desmos here in a minute. But at this point, it just might be a play thing where they've decided on a model with a reason, and they're now tweaking their model to make it fit. And in some cases, Lightning McQueen makes it, some cases he doesn't, which is an interesting thing too, is there just a single way that Lightning McQueen can make it? Or are there lots of different options if we tweak this and tweak that? Is it important to know the x-intercepts? Do they have meaning in this problem? Or the vertex, is the vertex important to know and have meaning in this context as students grapple with the situation? But this is an interesting thing too, in that so often students will say to me things like, oh, I love math. It's so black and white, cut and dry, right or wrong. And yet in this case, there could be lots of models that predict a successful completion of the jump, not just a single right, so-called right model. There's different forms that model could take, which is interesting and develops opportunity for some conversation and I think deep, rigorous thinking about the mathematics. But let's just say students are working, sharing. We've got all these possible situations. All right, then here's some guts. This is just for me in my brain. I love it. Thank you, Dr. Munson. All models are wrong, right? George Box, all models are wrong, some are helpful. So that's an interesting thing, right and wrong. Well, all models are wrong. So here is just the guts I made. Now in my brain, students are doing this, not me. So here's an example where in my brain, I made a factored form. And if you remember, I made the origin, the beginning part of the jump. And what that did for me in terms of the factored form is it made C 0. But I have C not 0. Maybe I adjusted it down here. Okay, anyway, the main thing I had to adjust then was, I made B 0. There we go. I made B 0 and I made C something else. Sorry about that. So I can now slide things around and see what happens as I adjust A and I adjust B in this case to 0, adjust C. I can see what makes it and what doesn't. But then maybe we do a more standard form over here in line 8. Maybe we do a more factored form or a defactored form in line 9. But in all cases, students should be prepared to articulate, communicate precisely what these models are telling them. So I've just shared all three, some of the guts here of the kind of the coding, if you will, of Desmos doing the work and students applying. All right, now, as this goes on, this is where, in my mind anyway, the rigor starts to get good. We're using technology, sure, to do some of the computational stuff, which I think is the right role for technology. Let the Desmos do a lot of the computational work and let the human do some of the interpretation work, like, which quadratic form did you choose and why? And maybe I would have students convert from one to another if I felt that was something I wanted to do at a moment, is, hey, why don't you convert yours to vertex form and then talk about what's the advantage of both forms? And then if, in my case, I placed the vertex or the origin at the end of the ramp. So if I noticed a student do that, I might ask them, what was the advantage of doing it that way? Not that you have to, but maybe there's an advantage. In my thinking there was. And then this is where it gets interesting in terms of, under what conditions is there a successful jump? Is there just one way that it could happen, or are there lots? Under what conditions is there an unsuccessful jump? Might as well talk about that too. Or suppose somebody came up with a standard form like this one. Here's the standard form that a standard form that produced a successful jump. And of course, I would want to ask students to tell me what the quantities mean. Keeping in mind that in my context, I had it set up so that X was a horizontal distance, Y was a vertical distance, and this actually is challenging. You'll see where this is going to become particularly challenging. For instance, in that standard form, what if we asked students to really deeply understand this factored form? We asked them to interpret the meaning of the parameters. I'm just going to pause there for a minute and let you just ponder. What would it mean in this context to say that the coefficient on the linear factor x there, linear term x, is negative 0.679? What would it mean to say that the a value is negative 0.07? And I don't mean in the sense of, well, since a is negative, the parabola opens down. I'm saying in this context, X is a horizontal distance, Y is a vertical distance. In this context, what do those numbers represent? I'm just pausing to let you think about that for a moment. Now, let me just tell you where I'm coming from on this. I'm thinking right now of, say, a college algebra course, and I know there's other pathways that can all be rigorous, but I'm thinking right now of a college algebra course, a pre-calculus course perhaps, and in that course, in those courses, it's common with linear functions, it's common for us to ask students to interpret, what does the so-called y-intercept mean in that linear function? What does the slope mean in the context of the situation for that linear function? Likewise, In my college algebra course, I want students to grapple with what do all the parameters of the quadratic mean? College algebra class. So what we might do is something like this. Suppose we just, I don't know if you saw my animation there, let me back it up. Suppose we ignored the quadratic term for just a moment. If f of x was equal to negative 0.679x, then as you can see on the graph, we would have Lightning McQueen blasting off of the ramp and then just continuing linearly, I guess, out into space. So that negative 0.679, given that the vertical intercept is 0, I forced my origin to be 0, 0. So intercept of 0, so he begins at x is 0 horizontally, y is 0 vertically, but we have a slope of negative 0.679. And I love this because what does that slope in a linear sense mean? Well, now remember the orientation here is if we move to the left, I'm talking about from the origin, move to the left, that would be a negative change in the quantity x. And then go up on that linear function, that would be a positive change in that vertical quantity. And so that ratio would be positive, negative, would be a negative quantity. So this line does have that negative slope initially of negative 0.679. So initially, at least, initially, Lightning McQueen is leaving the ramp at a rate of negative 0.679. That was a dramatic pause for you to fill in. What are the units? Negative 0.679 vertical feet for every 1 horizontal foot. Feet per feet. Isn't that awesome? I get excited about it because so often students in my calculus courses, just in their brain, every rate of change becomes something per second, something per hour, something per unit time. It's always a per time. They just, regardless of the situation, it becomes per time because that's the common experience. I want my students to slow down and pause and think about the quantities. And the quantity here would be negative 0.679 feet per foot initially, not just a velocity in terms of like feet per second. Ah, awesome. Now, that rate of change, though, is only the initial rate of change, as if that, you can see the linear direction there is the same for both the quadratic and the linear initially. But then that quadratic term is how the rate of change changes. Now, I know I'm dancing into the calculus realm, but I want my college algebra students to start thinking about rates of change, but also changes in the rate of change. So I don't have much time here today to get into how all that would happen, but I have ways with Excel and looking at it and go, hey, look at that leading coefficient. Well, half of it describes how the rate of change is changing, and it's changing in this negative way. So that negative 0.679 is changing in this negative way, and you have to kind of get in this wonky orientation because we're kind of reading this graph from right to left. I love it because you really have to stop and think about the quantities and not just go with the learned routines about, well, we always read graphs from left to right. And if a graph goes up, it's increasing. If a graph goes down, it's decreasing. In this context, I've got to think about this situation from right to left, not left to right. And I have to slow myself down and really think about the quantities. And so this initial rate of change in feet per foot is changing at a rate of half of that. And so we get the nice parabolic arc, and that's a fast way to get at it. Now, there's lots of other questions we could ask about the intercepts, about the vertex, I know, but I hope you can just see that there's a lot of places that we can go with this. All right, now bringing it back to, I have one more question. I don't have an answer to this one yet, but somebody brought up this parametric idea. Yes, another great question that students might be interested to know is, well, how long does it take him to travel this, what was it, 4/10 of a mile, horizontally speaking, across Carburetor Canyon? So to get some information, some data to help us explore that would be, I think, a fascinating place to take this as well in the idea of a rigor. All right, so now students are working. And sometimes, especially as I work with my K-12 teachers that I work with, sometimes it's this, there's this mindset of my job is to show students how to do stuff. And then I walk around and I make sure that they're doing it right. And notice in this case, it's kind of open-ended. There's a lot of directions one could take. And as students are working collaboratively in an active environment, I hope to accomplish this task, there might be some mistakes. And so, as Hattie and others have said, feedback thrives on errors, which we believe should be expected and celebrated because they are opportunities for learning. So our job is not to just walk around and make sure everybody's doing it right. I say our job is to walk around and engage with our students as they're actively involved in making sense of the ideas, applying the ideas, trying to solve this problem. And if there are places for improvement, we raise them up, have conversations around the room, because we all can learn. And this learning then can happen, according to Hattie and others, in 3 levels. Surface learning. There's this initiation of new ideas, the development of conceptual understanding, and then at the right time, labels and procedures are explicitly introduced to give structure to concepts. So put this in the context of Mater the Greater. We might be at a place where we've explored all the different options, but now at the right time, we're putting labels and procedures to these models, these quadratic models, but it might just be at a surface level. Then we keep going. Deep learning is what they call it, is about consolidating understanding mathematical concepts and procedures, making connections among ideas. So what I'm hoping in a task like this, that in the room you might have factored form people and standard form people and vertex form people, and we can make connections among those forms and those ideas. Students move to deep learning when they plan, investigate, and elaborate. Did you notice that one of my opening questions was just thinking about what you've seen so far? What model would you choose and why? Getting them to plan ahead. Now, you might change your plan, that's great, but we're looking toward this deeper learning to make a plan and then investigate and then elaborate, make some generalizations like, what do these things mean? And then Hattie calls it transfer learning, is the phase of learning in which students take the reins. Students take the reins of their own learning and are able to apply their thinking to new contexts and situations. The Mater the Greater context may help with exactly that, to give students the opportunity to apply their thinking to new contexts and situations. All right, but then I had to finish my 3-act task. Act 1 was get them engaged. Look at this thing and you go, oh, I wonder what happens. Act 2, we maybe get some measurements. We work towards solving the problem. We seek some information and some facts so that we can solve the problem. Now, let's say we've solved the problem. Act 3 would be, well, let's go back to the clip and let's see what actually happens.
Well, what happened?
You didn't make it. Well, see you later. Come on, guys, let's go.
Now, unfortunately, in my case, this particular Mater the Greater Pixar short does not show us the video of him, whatever happens next. They just, I don't know if you could hear the audio, but Lightning says, well, what happened? and Mater says, you didn't make it. So I don't know. It's not the best ending for at least what I would want. I would want to see my students model maybe work or not work or something, but it's just the way it is in Act 3 in this case. Whoa. So bringing it back then, rigor. A takeaway I would love to have you take away is, let's go back to our classrooms, our schools, our departments, whatever, and maybe have a conversation of what do we mean by rigor? And certainly we could use this from the National Math Summit 2018 as our definition of rigor. And then from that, let's build lesson design, let's build curriculum, let's build assessment, whatever, all the aspects of teaching and learning around this idea of rigor. So yeah, there's my email and a website and a blog if you're interested. And we have a couple of minutes. Laura, did you see any questions, or does anybody have a question or a comment you'd like to make? We have a couple minutes if you like.
I haven't seen any questions yet, but if there are questions, please place them in the chat.
Thank you.
I like that your presentation was rigorous.
Because it was exhausting and demanding.
Probably, no.
It was, I gotta tell you, from my end, it was super weird because I can't see anybody, I can't hear anybody, and so
I know. It's
I
crazy.
hope you're okay. Hey, April, I hope you all enjoyed the time. I appreciate your thoughts.
Okay, I just do want to give a reminder for the next session coming up at the top of the hour, lifting the veneer of racialization and context in community college mathematics by Ebony Zamani Gallagher. But seriously, if you have any questions, place them in the chat, and or email Scott. He will answer your emails.
I will for sure. Hey, I saw one, Laura. Where, what is it? Just flew on by.
The one about the NAID report.
Yeah, get the NAID
I
report
will find out about that, Carol. I'm not sure.
And then Steve, I don't really have a list off the top of my head of my favorite Desmos activities, but I obviously, you probably tell that I love using Desmos, but what I really love best is finding ways to have my students go in and engage in the, I call it coding. It's not really coding like programming, but in a sense it is coding Desmos to make it accomplish things like simulations. To think about, to actually get Lightning McQueen to move across that screen is a challenge, a rigorous challenge for students. But I love to try to find ways to get them to do that. So anything that's simulation, engaging like that, I love from Desmos. All right.
All right. Well, thank you, everybody. Great seeing you.
Yeah, great seeing you all. Thanks for coming.
Thanks for coming.